embeddability and its relation to Lorentzian geometry. It's a joint publication with Gerd in 2018, and I use overleaf online to produce slides, but the date is still 17th. So maybe it's because it's from somewhere. Today, I'll discuss briefly about CR manifold, explain the embedding problem, its relation to Lorentzian geometry, and finally our main results. So please ask me any question if something is not clear. We can discuss it in more details. So Gerd gave a talk on CR manifolds and embeddability a few weeks ago, but I start with this definition. CR manifold is a three-dimensional real manifold. D is a rank 2 distribution, and J is a complex structure. So you can see here, I don't distinguish between the set of vector sections on D and the D itself. So when we talk about vector fields, I actually mean a section on the distribution or tangent bundle or cotangent bundle. So I don't distinguish between set and the set of sections. So a CR manifold is strictly pseudo-convex. This condition is satisfied, X and J applied on X does not belong to D for any X, non-zero X. So if you complexify everything, I mean complexify D and also J, you can introduce D10 to be this set as a distribution of the complexified D, and the conjugate is defined just by having plus there. That's my CR distribution. And I introduced this round D as a spanner of D10, D bar for the conjugate, and complement these two vector fields by a real form of this form to have a frame for the complexified tangent bundle in this way. So we have D bar conjugate each other, and denote is a real vector field defined by the I times the commutator of D and D bar. And of course, we can look at the corresponding coframe of the cotangent bundle. Mu bar, lambda. Lambda is a real form corresponding to denote. And sometimes actually it's the contact form, and we refer to that as a contact form. And that's the coframe for the cotangent bundle. This choice of D bar and denote gives us these two conditions. Actually introduces three new functions, complex functions. This function C, alpha and beta. This function C is very important, and we will come back to this C later. This function C sometimes gives us some information about the CR structure itself. So it's very important, especially when we start talking about Sasaki structures. I'll give you maybe a characterization of Sasaki structures based on this function C and this denote here. So CR structures can also be defined in terms of form. Actually, Cartan defines it in this way. Physicists like Nurowski and Lewandowski like that because they are very good at working with forms. So if lambda mu and mu bar are linearly independent, and D is a kernel of that lambda. Lambda is the contact form. This is the real contact form. And D is the kernel of that. And if mu restricted to D composed with J is just mu, of course, restricted to D. So we refer to these three conditions as a CR structure. And we also have this relation here. So this relation, if you shift from lambda to F lambda, when F is real, and mu to H mu plus L lambda, H and L are complex, H can't be zero. Actually, we have a class of one forms. We have a class of one forms, And we denote this as a CR manifold, a three-dimensional real manifold plus a class of one form satisfying these three conditions. That's our, maybe not a new definition, but another way of saying, another way of defining CR manifolds. And actually we use this definition all the time in this talk. So now, what's the embedding problem? So if you consider a real hypersurface S in C2, it's a CR manifold with D to be defined in this way. TS intersected with J applied on TS. And J comes from C2, comes from the canonical complex structure on C2. This is that's the CR structure introduced in this way for the real hypersurface S in C2. Now, the embedding problem says, if we have a abstract CR manifold M, when the CR structure of this M agree with the CR structure of the real hypersurface in C2, when these two coincide, or when do they agree to each other? That's the embedding problem. So embedding problem can be expressed in a different way, slightly different way, by introducing two complex functions, phi1, phi2, satisfying this PD. And this condition is called functionally independent functions. Two complex functions satisfying this PD and also this wedge product. Function phi is called a CR function. And if we have two CR functions, phi1 and phi2, we can introduce the embedding in this way. We can introduce the embedding to be these two coordinate functions in C2. This is how we define it. So for the embedding problem, we always try to find two CR functions, phi1 and phi2, satisfying these two conditions. This is what we are doing in this talk, and also what we have done in the in that published paper. So some examples of embeddable CR structures. Real analytic CR manifolds are always embeddable. So if, of course, the problem is local. If you are in a chart, in a local chart, and everything is real analytic, you can, by Cauchy-Kovalevskaya theorem, you can prove that that CR manifold is always embeddable. Another good example that we are still working on that, and I think that's a very nice structure for producing Einstein equations, that's the Sasaki structures. Sasaki structure is defined in this way, actually based on the notion of CR structures, strictly pseudo-convex CR manifolds with a vector field Z transversal to D, where the lead derivative along the Z of J is zero. This is what we call Sasaki structures. This vector field Z is called infinitesimal automorphisms. They are always embeddable. And the reason is this, because if you consider two vector fields D and Z plus IDR, they form an integrable complex structure on M times R. And if you just look at the R equals 0, in that case, it is embeddable in C2. As I said, Sasaki structures can also be characterized in this way. If you have a CR manifold M, and you have a CR structure, and denote of C is 0, C does not depend on denote. The CR structure is Sasaki. Let me remind you the function C. The function C is this. This function C. If this C does not depend on denote, and you have one CR function, it is Sasaki. This is what it was expected, but it took a while to prove this statement, because one side is clear. If it is Sasaki, it does not depend on, C does not depend on denote. But the other way, the converse was a bit challenging at the first time, but now we can say this criterion or this characterization. So not all CR manifolds are embeddable. The first counterexample appeared in a Hans Levy work in 1956. And Nuremberg proved that this equation has no solution when D is this operator. X, Y, and U are coordinates in the real manifold M. When D and if you expand this operator, you get D1 and D2. And it says D1, D2, and the commutator have to be linearly independent. So not all CR manifolds are embeddable, and this is probably the first counterexample in this context. Another notion is the canonical bundle. Is a canonical one, which was introduced by Lee, and Jakubowicz used it a lot. So maybe based on our definition of CR manifold M and the class of one fold, I should say the canonical bundle is just generated by lambda wedge mu. That's a complex two-form. And the non-vanishing closed section is defined in this way. Of course, exterior derivative of a multiple of this form has to be 0. And if you expand this, it gives us this relation, which is very important. And this function C is again that function C, which plays a very, very important role in, I think in all places, this function C is very important. So now one theorem which was very important and helpful in my PhD thesis was Jacobi's theorem. It says if you, as I said, the problem is local. Around some point of the CR manifold M, if you have a CR function phi which satisfies this condition, and also this equation, this PD has a solution, then the CR manifold is embeddable. So if you have a CR function means, having a CR function means this equation is satisfied. If you have this equation, and this equation, if you could solve these two equations, the embedding problem is solved, which is not that easy. So this canonical bundle, the non-vanishing closed section of the canonical bundle can be stated in physics as a Maxwell equation. I'll introduce that in next slide. So here, Nurowski actually introduced or observed that notion and the relation with the CR structure. That's the Maxwell field. And I think, please correct me if I'm wrong, because we use electromagnetic field and Maxwell field for this notion. So we don't distinguish between them. If they are different, are they different for you, Jock?
Sorry, say that again.
So for the Maxwell field and electromagnetic field, we don't distinguish between these two. Are they the same also for you?
Yeah, no, that's right. That's called electromagnetic duality.
Yes, exactly. So
they're the same thing. You just have to exchange what you mean by electric and magnetic field.
Yes. We use similar terminology for both of them. So,
Masoud, can I please ask a question too? Just if you could just back up to the previous slide.
This one?
Yes, this one.
Yeah.
Now that in that window there with canonical bundle, are you saying that the second bullet point where there's a complex function f satisfying that relation, that's a necessary and sufficient condition for the existence of a non-vanishing closed section? Yes.
Yes.
So
If you, yes, exactly. So if you have this function, yeah, it satisfies the, yes, we have the left hand side, yes.
So that becomes the necessary and sufficient condition for embeddability using Jakobowitz as a result. The existence of F becomes the necessary and sufficient condition for embeddability.
Yes, yes, exactly. If we have one CR function, yes. If we have one CR function, yes.
Okay.
If we have one CR function and this condition, yes, it implies embeddability.
Okay.
So what were lambda and mu?
Again?
Can you just remind, what was lambda and mu? So lambda wedge mu is...
so lambda and mu. So we started with this D10, introduced this spanner. Yeah. And mu is the dual to this, and lambda is the dual to G naught. And lambda wedge mu is the generator of the canonical bundle. Lambda wedge mu here is the generator of the canonical bundle. So having a closed section means you have an arbitrary function f satisfying this equation.
Right.
Does that make sense to you?
Yeah, I think so.
Very good. So officially, Maxwell field or electromagnetic field is defined in this way: a real two form F, which dF is the same as Hodge star to be zero, Hodge star of F. So and just we are in 4 dimensions. So the Hodge star of real two form gives us another two form. So we are in 4 dimensions. So we have some definitions here. In the complex, we actually following Nurowski, the complex case is F times Hodge star of F. It has this property. Of course, has to have this property because of these two conditions. This is one property. Hodge star of the complex electromagnetic field is minus I times F.
Sorry, Masoud, what does it mean Maxwell field aligned with the CR structure?
Yes, this is what I have introduced here. Maxwell field aligned with the CR structure is this one. F lambda wedge mu, because we can prove that.
So that's what you're identifying curly F with F lambda wedge mu?
Yes, exactly. This is Nurowski's terminology to say a Maxwell field, which comes from the structure, is introduced in this way. And we observed is nothing but the closed section of the canonical bundle. And we don't need to talk about Maxwell field for the embedding problem. This is it was our observation.
The second point follows if F, the original Maxwell field F, is anti-self dual, though, isn't it? If star capital F, that's the simple F, not the script F, is minus F.
And that's right. Yes. And not every F would be anti-self dual. That's actually an addition.
Yes, exactly. Yes.
And are you saying that F lambda wedge mu is also anti-self dual? Is that an identity or is that a condition?
No. I think it has to satisfy this condition.
It has. Okay, so it's another one.
Yes, has to satisfy that condition.
And is that to do with the fact that it's a section of the canonical bundle?
Yes, actually, yes, that's a closed section of the canonical bundle. And if you remember, I introduced the canonical bundle in this way. So the canonical bundle is this. So generator that's the generator, lambda wedge mu. So F multiplied by this is actually generates the canonical bundle.
And this is a Lorentzian manifold with a metric.
Which one?
Oh, it must have a metric. Is the metric flat or is it unspecified? Or?
So far, canonical bundle has nothing to do with the metric. It's just a 3-dimensional manifold, CR manifold, and lambda and mu. We don't have any metric at this stage. But
so then what do you mean by Lorentzian?
So
because I always thought Lorentzian was to do with the signature of a metric.
So yes, exactly. So Lorentzian here, I mean plus.
But you must have a metric because you're talking about Hodge duals too. So
yes, I introduced that here. Yes, please look here. Here I don't talk about any Hodge star or anything. I just introduced.
That's right. Yeah, it's the next slide that I was.
Yes. Yeah. Next slide, I introduced the. Of course, we need a metric to talk about the Hodge dual. Yes, that's correct. And because of that,
and is that metric just 1, 1, 1 minus 1, or is it any metric with that signature?
No, it could be this one, or of course, we usually work with this. And I think in the complex case, it becomes 1, 1, 1, 1, 0 elsewhere. 3, yes. So I'll introduce this the frame in the next slides, and you will see how it looks like.
And
this F. Yes. Is this F actually a function, or is it sort of a local function?
This function, this F, it's a complex.
Yeah, is it actually a function? Is it globally defined, or is it?
No, it's a local. It's a local function.
We seem to have missed a beat here at some point. You've started out talking about a three-dimensional CR manifold, and you've moved on to look at a four-dimensional Lorentzian manifold, but it's clearly related to the CR manifold because you're still talking about the CR structure.
Not yet.
So how is this script M4? How is it related? How is it defined in terms of the original three manifold M?
So
that's the Sasakian structure, is it? Is that what you're implying here?
So in this slide, I don't need any metric. I haven't started Lorentzian. So here I said Maxwell will align with the CR manifold.
So all right. So if we go back to that M cross R that you talked about previously.
Yes, exactly. So
okay. So that's actually the underlying topological space of this Lorentzian manifold is M cross R.
I'll introduce that a bit later. Maybe it was a bit soon to talk about Lorentzian, but I wanted here to define the electromagnetic field in a formal way. Yeah. This is how I started with. So at this stage, I haven't talked about the relation between CR manifold and Lorentzian geometry yet. I haven't started yet. Does that make sense?
Yes, I mean, it'll come together, obviously, in the next slide, but it just seemed a little bit of a disjoint jump from the CR manifold to the Lorentzian manifold, but I think most of us know where you're going. So
the idea was to talk about CR manifolds, then Lorentzian geometry, and then the connection. Yep. Maybe people would like to have it in a different order. So at this stage, again, I don't talk about CR manifold, just the Lorentzian geometry and its properties, and then I will talk about the relation a bit later. So if M, you have a four-dimensional Lorentzian manifold with a foliation of integral K of a real vector field K, null vector field K. We introduce K perb on K and introduce these two complex eigenspaces like this. We complexified S in this way, minus I and I eigenspaces, and we call these alpha planes and beta planes. These are some geometric meaning that does not depend on the frame, and sometimes we work with alpha planes, sometimes with beta planes, but are actually behave similarly. So that's one notion. So alpha, and I think we had a long discussion about alpha planes with you, Adam, about these alpha planes and beta planes a long time ago. So if you have a Lorentzian manifold with K to be null, we introduce this frame. L is a real null frame, sorry, vector. So let me write the metrics carefully here. So if I write the matrix it is of this form. 0, 0, 1, 1, 0, 0, 0. And of course 0 here. That's the matrix corresponding to this complexified complex frame, or what is called by people tetrad, if I pronounce it correctly. So L and K are real, E1 and E2 are complex, and we have this relation between them. And if you remember, this K10 is now spanned by E1, which is complex, and K01, that's the conjugate of K0 by E2 and K. So when we say Ricci flat, so we have a metric, Lorentzian metric G. We have these two spaces, K10, K01, and we can talk about the Ricci tensor on these two sets. So corresponding to this frame, R11, R14, and R44 are the components of the complexified Ricci tensor. So when we say the metric vanishes on the complexified alpha plane, actually we mean R11, R14, and R44 are 0. And similarly, because these are conjugate, because 1 and 2 are conjugate to each other, we automatically have this. And of course, 4 is real. We have this condition. This is what we need for the embeddability, but for a special, very special metric. So, as I said at the very beginning, we need two CR functions. One CR function has been known, finding a CR function is known to physicists for a long time. So they link CR manifold to four-dimensional Lorentzian geometry and look at the Ricci curvature of the alpha planes. And once you have this condition, I mean, vanishing the Ricci curvature on the alpha planes, having these three components of the Ricci curvature to be 0, then we can it's a very nice observation. It gives us a CR function. This is exactly what we need. So we link CR manifold to four-dimensional case, as Adam said, by multiply that by R, looking at the line bundle of the CR manifold, introduce a metric there, look at the Ricci curvature. If it satisfies these conditions, it is embeddable. The underlying CR manifold is embeddable. So this is how they connect CR manifold to Lorentzian geometry by shear-free congruencies or shear-free geodesic congruencies. So you have a four-dimensional Lorentzian manifold, integral cap of a non-vanishing vector field K, which is null with respect to the Lorentzian metric G. And having this condition, it is almost conformal Kling. So we have symmetric product, this form phi. But theta is a form generated by the Lorentzian metric and the null vector field K. This condition is called shear-free condition. Maybe precisely, I should say shear-free geodesic congruence, something like this. But we just refer to that as a shear-free vector field or shear-free condition.
Sorry, Masoud, what's the upside down wedge?
Sorry, say it again.
What's the upside down? Should that be a wedge, or does that mean something?
Symmetric tensor product.
Oh, okay. Yeah, okay, cool. Yeah, makes sense.
maybe you define it
Yes.
without half. This is not wedge, it's symmetric tensor product.
Yeah, that makes sense. Yeah.
So 1 and 2, these two conditions, actually it may be simpler to look at this way. K is conformal killing on K pair. Because K is null, because K is null, K also belongs to K pair. So if K is conformal killing on this set, we can say K is conformal killing.
So should that be the Lie derivative with respect to K of G being proportional to G? Is that G restricted to K per?
No. In this case, no. Or do you mean here, or in the shear-free case, or here?
Well, I mean the equation you got, that is Lie derivative of K of G is rho G.
No, actually.
So how do you? But in the 2 lines above, you've got an equation which says the Lie derivative of G is not just.
The reason is this, because K pair, because K belongs to K pair, and this part automatically vanishes. Does that make sense to you?
So are you saying that 2? So you've got 1 and 2 you're basically saying if I have 1 and 2.
Yes.
Then I have the Lie derivative of G with respect to K is rho G. So in other words, if K is null,
K is null.
The equation in 2, you drop the symmetric tensor.
Exactly. And I think you're right. If we restrict everything to K-PEP, of course. If we restrict everything to K-PEP, yes, we just drop the second part. Yes. Thank you.
Yes, that's important. Otherwise, the initial definition of shear-free congruence could be replaced by that simple equation there. There'd be no reason to give conditions 1 and 2. You just give that consequence.
Right.
Yes. Yeah.
Right.
But that's
that's basically what I was wondering. Yeah.
That's not what you mean, though, is it, Masoud? So it's, as Jock says, you get that simpler equation when you restrict to K-PEP.
To K-PEP, yes.
Yeah.
Exactly. So K is called shear-free vector field, and G with respect to vector field K.
And sorry, Masoud, so shear-free. I should probably know this, but how do I see what's shear-free mean here?
Actually,
what's the name? Where's the name come from?
Actually, there's a very nice book by O'Neill about the notion of shear in physics. And I have proved that in my PhD thesis. I think the notion of shear in physics has to do with shear and expansion and all of these coefficients in physics. They have their own definitions.
Yes.
But
so I think my understanding of it is very basic. I don't know much fluid mechanics, but it's sort of, if you have a box of fluid, then there are all the forces going through the box, and the shear one is sort of the one that's what's the word?
So the
parallel to the I don't know, waking up.
Yeah, I have to again think about it. So the notion of shear in physics, so it is known to them. But for me, it was a bit challenging to understand these two relations, but I still forgot the relation in these two. But I have it in my PhD thesis.
Yeah, I think it's deforming forces. If we travel along that vector field K, then the shape is basically preserved. We change the scale, rows change the scale, but the metric is not deformed. The shape is not deformed.
Is it a condition that, I'm sorry to add this on the end, but it's just a thought that occurred to me. Is it something that can be expressed in terms of the curvature, say the Weyl curvature? If it's restricted to K, will vanish or something like that? Is Is there any way of formulating it in terms of curvature, the shear-free condition?
I haven't thought about it, but in terms of Weyl curvature,
well, you would.
Yeah, I think there must be, because there's certainly conditions that come from conformal Killing vectors that somehow imposes relations on the curvature tensors.
Oh,
I don't know what they are.
Haven't seen that, yes. But of course, we have Galbraith-Sachs theorem here. If we have a shear-free vector field, which is this condition, some of the Weyl components vanish actually. That's the Galbraith-Sachs theorem. And it happens only when K is shear-free.
Sorry, which theorem is that, Masoud?
Galbraith-Sachs theorem.
Galbraith-Sachs. Oh, yes. Okay. Yeah.
That's the famous Galbraith-Sachs theorem. Yes. So if we have a shear-free vector field and some of the, actually, let me say it precisely. If we have a shear-free vector field K and these three conditions on the alpha planes vanish, the two components of the Weyl curvature vanish. That's the observation by maybe a kind of generalization of the original Galbraith-Sachs theorem by Gerd and Nurowski. They said if the complexified tensor vanishes on the alpha planes and vector field K is shear-free, yes, two components of the Weyl curvature vanish.
Okay.
So now this is where we have to connect CR geometry and Lorentzian geometry, where Adam mentioned it earlier. So if we have a CR manifold M, and if you look at this line bundle, Cartesian product, we introduce this metric this way. So sometimes we don't distinguish between forms in this way. We just denote it by mu. If you look at the projection from M times R to M, so the forms mu and lambda are defined on the manifold, three-dimensional manifold. We lift them up to the four-dimensional case in that direction. That's direction R, and we introduce this metric. P is a real function. P is the coordinate of all of them. So if I introduce on M some coordinates X, Y, and U, or sometimes I use complex coordinates Z bar, and U. So we introduce this form. P is a function of all variables, X, Y, U, and R, and also H. And also W are three functions. We call this function a shear-free metric. The reason is this, because K d by dr is shear-free. If we do some computation, some algebraic computation, you get this condition. You get this. And it is obvious that it is null, K is null, and K is shear-free. That's the general shear-free matrix. We have two nice examples. Fefferman metric, which is so important in CR geometry and complex analysis. And this is what we have introduced in our paper. So for Fefferman, we can talk a lot actually. So it is a determined function. So W is determined. C is the famous C. Alpha and beta come from that alpha and beta at the very beginning. So let me show you. Where was it? Yes, this function C, alpha, and beta. So So Fefferman metric is of Petrov type N. I have said that here. Petrov type N is never Einstein. I mean, if you compute the Ricci curvature, it's never Einstein. But if you put a conformal factor in front of it, yes, we can say it's conformally Einstein. It's the result by Philippe Leitner, and we also proved that independently in a slightly different way. What we have introduced in our paper is this metric. So why W is of this form? As I said, by the Galbert-Sachs theorem, if you have a shear-free vector field and the Ricci curvature vanishes on the alpha planes, implies two components of the Weil curvature vanish. Vanishing those two components implies W to be of this form. So we have to, not exactly this form, in general implies this, Ix plus Y. But in the process of producing the theorem for embeddability, we noticed that this part has to be very similar to the Fefferman metric. That's the most important part of this theorem.
Masoud, if I could just very quickly ask a stupid question. The alpha which appears in your formula here, which comes from the original alpha and beta,
yes.
Are we supposed to assume that has some connection to the idea of alpha and beta planes, or is that just a coincidence?
No. Sorry, maybe just a coincidence. Yes, coincidence.
Okay.
Nothing to do with the alpha and beta planes. Just a complex function.
Okay. And you're going to explain why there's no H in the definition of the Fefferman-Robinson-Trautmann metric, I guess.
The reason is this, because H is not determined. So we don't care about H.
Okay.
Because W was the most important part. And H can be determined for different purposes. If you are interested in Einstein metric or Ricci-flat metrics, it gives us some formula for H. So shear-free vector field is geodesic, meaning this. CR invariant, all of these three matrices are CR invariant. It means if you, instead of mu and mu bar, if you choose instead of mu and lambda, if you pick another representative and you do the computations, the matrix is still in the same class. So that's the meaning of being CR invariant. Fefferman metric is of Petrov type N, as I said, never Einstein, and conformally Einstein, having a conformal factor. It is subtle. For some people, they say it's never Einstein, meaning that the conformal factor cannot depend on the R coordinate. So if you have a conformal factor just depending on X, Y, and U is never Einstein. Fefferman is never Einstein. But if depends on R, yes, we can, in some cases, we can prove that it is conformally Einstein. So maybe it's good to mention Robinson theorem also here. It says if you have a shear-free congruence, like that vector field K, there exists, should be A, not N. It was an electromagnetic field. So Maxwell field, and the converse is also correct. And I think in our recent publication with Dmitry Alexeyevsky, Gerd, and Andrea Spiro, we proved this theorem in high dimensions in both sides. And it was our yep.
Sorry, Masoud, in the higher dimensional case, you mean higher space-time dimensions, but it's still
yes,
F2,
exactly.
it's still
so
S24.
We have 2n plus 2 Lorentzian.
Yeah.
Lorentzian. with 2n Keller Sasaki.
And you were talking about Maxwell fields that are self-dual or anti-self-dual, but that's not the case in this high-dimensional case because obviously the Hodge dual.
High dimensions, notion of this duality and how to actually generalize this notion was a bit subtle.
Yeah, right. So the generalization of the anti-self-dual condition is
yes.
Okay, that might be interesting. Yeah.
But I think it was a good observation in higher dimensions as well.
Right.
So it was good to mention this. And now, two good examples maybe for physicists. So we have two good examples of shear-free metrics, top knot, and also K. So it's.
I mean, how good is the Taub nut name?
Say it again.
I've never seen it amazing.
I couldn't get you.
Hey.
I couldn't hear you. Sorry.
The Taub nut, like it's such a good name. I mean,
it's not
just to write a good paper. You need to come up with a good name for something, and then people take notice.
Maybe 3, 4 names.
Yeah, but they realize, if I put Taub there and then the initials of the other 3, we get something unique, as opposed to T, N, U, and T or something.
Maybe.
Who are the other 3 who are initialed there, N, U, and T? Do you know, Jock? Or?
Oh, give me one. I can't remember. Look up.
Not to worry.
N is Newman.
Newman, Tamburino, and Unti. I'm not sure how you say it. Theodore Unti.
That sounds right, yeah.
I mean, it was originally discovered by Taub in 51 and then extended to bigger spaces by the nuts. So I guess that makes the initials makes sense. Anyway, sorry, that was.
That's okay. Tom, actually, we prefer to write these two metrics in this way. I mean, using the Kähler potential. So the Kähler potential here, if you ignore 2 and B, P is a constant, positive constant, is just the Fubinic to the Kähler potential. So here we have a Kähler metric, rescale it, and this part is known in this way. Lambda is introduced by the Kähler potential in this way, and this way is introduced that way. And we also generalize this in higher dimensions. So if you have 2n Sasaki Kähler-Einstein metric, which is this part, and you extend it in this way, it gives us an Einstein metric in 2n plus 2 dimension. Computations are tedious, are very long, but I think we ended up with a nice result there. And in the K metric, and not only us, so there are also some other people like Arman. The first part is Iranian, but the second part is French. Chabet, I think Adam knows him. I don't know very well or not, but he knows him. So he also produced such metric in high dimensions in a slightly different way. So in K metric, the Kähler potential is in this way. This is the Kähler potential. And the metric is introduced in this way. We are still working in high dimensions case, which is very long procedure, and we are still working on that.
Masoud, with these two examples, the original ones, the Kähler potential K in each case, is that defined? I mean, in the first case, that Kähler potential is the potential of the Fubini-Studi metric, as you and Gerd have pointed out before in other talks. So is this metric, is the Taub-Knut metric G defined? You're looking just at a local definition, are you? But is it something that can be defined globally on say, CP2 or something like that? Does the Taub-Knut metric have a global extension, or is it just something that you construct locally from this potential?
I don't know anything about the global results.
I think there is a global extension. Because there's singularities, and you need to worry about the singularities.
Okay, but are they just point singularities, or?
Yeah. Nut points, Adam. They're nuts.
Nut points. That's great.
That is the literal terminology, I think. And I think what Nut showed, Newman, Tamburino, and Unti, is how to extend the metric across those singular points.
Oh, removable singularities. That's very nice to know.
So the answer is no. So is the answer no? There is no such extension for the global case?
So say that again.
Jack, do you mean the answer of Adam's question is no? There is no global extension of Taub-Knut?
No, there is, yeah.
There is.
There is an understanding, yes.
And so this is an extension to 4 real dimensions, 2 complex dimensions, which means we're looking at CP2.
I think topologically this space is actually R cross S3.
R cross S3.
Yeah.
Okay.
So I think how Masoud's written it is S3 sort of written as a Hopf vibration.
Yeah.
And so there's a circle over the P1, which has the Fubini-Studi metric.
So R cross S3 can be made diffeomorphic to C2 minus the origin. So that's
right. So
you're talking about a complex structure or a Kähler structure on C2 minus the origin, which is obviously not the standard one. So it's okay.
Right.
That's very interesting. All right.
Yeah, I think I could probably look. Yeah, that rings a bell. I can probably try and dig that up.
Yeah, that's interesting.
I'll have a look after it and I'll let you know.
All right, now finally I can talk about the embedding problem, embedding theorem. So our main result is the following. If you have a CR manifold, M, it is embeddable if there exists a representative of the Fefferman-Robinson metric whose complexified Ricci tensor vanishes on the distribution of alpha planes. So if we have such metric, which R11, R12, and R44, sorry, 14, not 12. 14 is 0. So if we have a representative in the class of Fefferman-Robinson metric which satisfies this condition, the underlying CR manifold is embeddable. And the idea of the proof is the following. So if the CR structure is embeddable, there exists a closed section of canonical bundle. It's not that difficult to prove. So first of all, if CR structure is embeddable, there are 2 CR functions. You can pick one and introduce mu to be d of one of the CR functions zeta, which is closed. And it makes life much easier in this case. There exists a closed section because df wedge d zeta is 0. Now the closed section becomes this. And this d is not just rounded. You can write it in terms of coordinates z and u. You can write it in this way. You can, it depends, maybe it's not a correct notation, but it depends on z and u. So if it is embeddable, there are 2 CR functions, closed section exists, And then you can introduce these two functions, not two, but four functions in this way. Once you introduce these functions, and by doing some computations, you can show that the Ricci-Kevich vanish on the alpha planes. One side is this way. The other side, if the complexify Ricci tensor vanishes on alpha planes, it gives us, that's the approach by physicists, it gives us one CR function. And once we have this one CR function, by looking at the equation of the Ricci equations, we get this equation. This is equivalent to R24 to be 0. So this equation does not automatically give us a closed section of the canonical bundle. We have to get rid of this T. And how we do it? How do we do that? Actually, we look at a different representative of lambda and mu. And because everything is geometric, the next step for the neo representative, T becomes 0. And it gives us a closed section of the canonical bundle. So we have a CR function which comes from this part. And from one of the equations, we get a closed section of the canonical bundle. And consequently, the CR manifold is embeddable. That's by Jacobi's result. That's the end of this theorem. And so we have some other things to do, but we need time. We need time to do that. So that's one question. Trautmann conjecture was, if you have a closed section of the canonical bundle, just you have a CR manifold, closed section of the canonical bundle, does it imply embeddability? So many people have been interested in this question, people like Ebenfield, like Jacobowitz, and we still don't know what happens to them. So maybe for a shorter period, this is a better project. Geometric properties of this metric. And maybe if we could some Einstein metric in this family of different types. So we answered this question partially in our recent work with Gerd and Daniel, and which has been submitted for publication, but still a lot to do. And it was the end. Thank you for your attention.
Thank you, Masoud. Any questions?
So Masoud, that the hypotheses of your embedding theorem rely on the fact that the Fefferman-Robinson-Trautmann metric, like the Fefferman metric, is a canonical metric. It always exists on a CR structure. Is that right?
Are you referring to Fefferman or Fefferman-Robinson-Trautmann?
Well, in particular, Fefferman-Robinson-Trautmann. That's a metric which you can always obtain. It's just a question of whether it has this extra property of vanishing on the alpha planes.
Exactly.
Yeah, that's very nice.
Thank you.
Any other questions? I mean, we've already asked them quite a few. So just a comment about Taub-Nutt again. So Hawking found Taub-Nutt very interesting. So he wrote down a Euclidean version of the Taub-Nutt metric. And that's interesting because it's what's called a gravitational incipon, which means that the curvature is self-dual. So that gives it a lot of symmetry for hyperkähler manifold and all sorts of wonderful things. And then there's a whole host of similar sorts of solutions, like Gucci, Gilkey, Hansen have similar sorts of four-dimensional Euclidean solutions. But of course, for Masoud's thing, you need you really need a Lorentzian signature, I think. So.
Yes, yes. One of the good things, maybe it is nice because the underlying Fubini is also Einstein.
Yeah.
Which is not the case in K-metric. So because of that, the K-metric is much more complicated.
Right.
So we have been working on the generalization of K-metric a long time, and that's because the underlying structure is more complicated. It's not Einstein.
Just apropos of Jock's comment there, do physicists have a motivation for considering these Euclidean analogues of these special metrics? What's the motivation for considering them in a Euclidean setting?
Well, compact, rich, yeah. So they're explicit examples. And they're solutions of Einstein's equations. So, you know, they sort of form models, if you like, in more complicated theories, where because you have an explicit metric, you can actually compute things.
I'm just a bit confused by the use of the term Euclidean here, though, because, I mean, if we're talking about solutions of Einstein's equations, aren't we talking about Lorentzian metrics?
Oh, not necessarily. Yeah. So, I mean, there's the generalization of Einstein's equations to Euclid. There is a generalization of Einstein's equations to Euclidean metrics. And so there's an Einstein tensor, and it's basically the same thing, Ricci tensor minus some multiple of the Ricci scalar. And because these metrics are self-dual, showing this as a solution is actually extremely easy.
Is actually what?
It's extremely, because the metrics are self-dual, so because R is star R, showing this as a solution is actually extremely easy. They're just examples with lots of symmetry, and so you can actually compute things that would be quite hard in a quantum theory that would otherwise be impossible to do, you know, with some example with less symmetry. So they're not really physically realistic because they have too much symmetry, but they just form really nice toy models.
What intrigues me is that surely as soon as you move away from a Lorentzian metric and consider something Euclidean, you're moving right away from physics, basically, aren't you? So,
well, it depends what theory you're thinking about. So if you're thinking of string theory, then all of our stuff is tied up with these compact Euclidean manifolds. And so we still have a Lorentzian space-time, but it's somehow very weakly coupled to this internal.
So when you say Euclidean, you mean more generally Riemannian. The compact dimensions are governed by a Riemannian metric, not a Lorentzian metric.
So yeah, okay. So that's quantum field theory. No, yeah, that's right. Yeah.
Okay, so that's very interesting. So the compact dimensions in these supergravity theories are actually, we're talking about Riemannian metrics, not Lorentzian metrics. So.
Yes, absolutely. Yeah. So I spend so much of my time thinking about just Riemannian. So I'm using the right word now. Riemannian metrics, as opposed to Lorentzian metrics. So I have to do a little double take when I see factors. You know, self-duality involves now and I.
Okay.
That's right. And yeah, it's actually, yeah. When you try and think about a quantum field theory on a Lorentzian space-time, it is much harder than a Euclidean space-time. And so there's this very dodgy thing that you do when you learn about path integrals. You analytically continue. So time becomes imaginary so that you can think about Euclidean things. And Riemannian things. And then when you're in a Riemannian space, these path integrals, which are unwieldy beasts, start to have better convergence properties. So that's part of the, you know, that's one physical, well, not physical, but sort of physical way that you end up studying Riemannian things is, look, the integrals actually converge as opposed to trying to make sense of, you know, boundaries and stuff. But yeah, for me, it's more, this is the internal space that we've been talking about of this supergravity theory. There is a Lorentzian space-time, but it's sort of uninteresting.
Of course, Einstein might beg to differ, but
yeah, I think everyone pre-1970 would beg to differ.
But I guess that sort of indicates why people like Einstein and the early people working on unified field theory must have had great difficulty, because they were trying to do everything with Lorentzian metrics.
That's right, yeah.
And the unification with quantum theory was obviously, I mean, Dirac's achievement was to unify special relativity with quantum theory. So he wasn't, that isn't working with compact dimensions and Riemannian metrics, but it's...
there is certainly working, everything is okay if you're in flat space-time somehow, in a way. The theory works, you calculate these things, mathematically it makes no sense, but you just turn on your collider and you check the answer. And the answer is correct. So it must somehow work. The problem is making sense of curved spacetimes. Then you're in all sorts of strife. And it was sort of Hawking and Gibbons and these guys in the 70s who were studying GR that realized, look, it's much more sensible to think about Riemannian metrics. And we can wave our hands about this with this analytic continuation thing, but then I can start to do some quantum mechanics in a curved spacetime. And, you know, there, I guess the experimental testing ground is cosmology somehow. Yeah, I don't know. I'm talking about things that I don't know an awful lot about, which is always dangerous. But, yeah.
That's all right. In the land of the flightless bird, the one-winged man is king. So
that's exactly right. No, it's good stuff. Yeah.
Thank you, Masoud. That was a wonderful presentation, and gee, it's come such a long way. It's now a really beautiful theory that you're developing here. So you and Gerd and your collaborators.
Thank you.
Yeah, absolutely. Yeah, that was a really nice talk. Awesome.
So if